So after the introduction last week, we will start with the real work. And this is, as I announced last week, this is looking into the method of ray tracing. What is that, and and then how do we do some of the computations? So first of all, ray tracing is one of the essentially two rendering algorithms that we have in computer graphics. Rendering is the method of taking a 3D scene description. We'll talk about this in a second, as input, together with a camera, virtual camera description, and generating a 2D image of what this virtual camera would see, right, if it were in that real environment. And there's, as I mentioned, two basic algorithms. Ray tracing is one of them, and the other is rasterization. Ray tracing takes a declarative scene description. So that means a description of all of the surfaces, the light sources, the optical properties. We'll go through that today. Takes all of this and then performs a physically based simulation of how light is being transported around in this 3D scene. Because at the end, what your camera sees is the light as it bounces around in the scene, and then from all the objects in the scene bounces towards the camera. So we're interested in, right, given that we have some light sources in the environment, how the light bounces around in this scene and then eventually makes it to the camera. Now this is a declarative scene description with an implicit model of how to compute what the image looks like. That is very different from a rasterization approach, which we'll also talk about in this lecture, but as I mentioned last week, more towards the beginning of next year, so in January. Rasterization is a more traditional and also an imperative drawing method or rendering method. Essentially, it takes a scene description and then describes how you render each object, each surface, typically triangles, how to render the scene one triangle at a time onto a screen. And it actually, by itself, doesn't have any method to deal with lighting simulation. We will talk about this. So global illumination effects, shadows, and many other aspects, even transparency, or let's say at least refraction, so glass surfaces, are pretty hard to do in rasterization and actually require methods on top of rasterization. It can be done, but it's essentially stuff that is on top of rasterization. It typically can't be done accurately, but is some sort of an approximation. But as you see in today's games, you can have amazing effects, and they run at high frame rates. However, the cost of doing these simulation or these approximation in rasterization can be tremendous, and the teams that are developing these game engines and the rendering algorithm in these game engines are typically fairly big teams. Ray tracing you can actually do yourself, at least in the simple way, and you will do it yourself in this lecture. Okay, so let's go to the next slide. So scene description, I already talked about this. So this consists of, on the one hand, the geometry, the surfaces, geometry of surfaces. At least for now, we are ignoring anything else. So there are volume objects, some things like fog, often called participating media. We're ignoring them. We're assuming we only have surfaces, which is the most typical thing you look at, right? I mean, what you see is typically surfaces of some objects. So we need descriptions of the 3D geometry of these surfaces of the objects, and we typically describe these objects with geometric primitives. Typically in computer graphics, essentially everything is described in terms of triangles. We could also use polygons and spheres and other also curved surfaces. We'll have a lecture on that. But eventually those curved surfaces, something like spline surfaces, something like NURBS or other, are eventually turned into triangles, both for rasterization as well as typically for ray tracing. Even though for ray tracing, there are algorithms to deal directly with curved surfaces, such as also including subdivision surfaces. So there's this whole notion of how to describe the geometry, and we will look into this to some degree in this lecture. But as I mentioned last week as well, there is actually a separate course on geometric modeling that goes into all of the detail, not all, but most of the details of geometry. So once we have the geometry of the scene, we need to know how does light actually interact with the geometry, right? At the end, we're interested in the light that is being reflected from these objects. So obviously that involves the color, but not just objects typically don't just have a single color. Well, maybe metal, maybe plastic has, but most surfaces have some structure on top of them, right? So this could be the wood grain on a table, or the pattern on a carpet, or on the walls and stuff like that. In terms of physical effects, it involves things like how much light is being absorbed, how much light is being scattered. So that's reflection and refraction. There could also be scattering within the surface, even though we will ignore this for most of this lecture because it's kind of an advanced topic. And we describe these properties of geometry typically as materials. And we'll go into much more detail what this looks like. In particular, we typically define certain types of materials, such as diffuse materials that scatter light in all directions. So a white wall is a typical example of a largely diffuse surface. We have mirror or glass surfaces that, let's say, perfectly reflect light like a mirror, or perfectly refract light like a glass surface. But we also have in-between objects that we typically call glossy materials. And again, we'll go into much more details for this later on. And I'll just switch on some light here so hopefully the illumination is better. By the way, if there's any questions, please feel free to interrupt me either on the audio channel or by posting on the chat. So once we have the geometry and the optical appearance of surfaces, we're obviously have to deal with illumination. So that involves like the position and the emission characteristics of light sources. And we're not only interested in the light sources themselves, because at the end, the illumination doesn't just come from the light sources, but also from the light that is reflected off of all the other surfaces, right? So the wall here behind me in the video does illuminate me because light bounces off of that. Light from the light sources bounces off that wall and does illuminate me. However, it turns out that these secondary effects, so light that doesn't come directly from the light source, is actually pretty hard to compute. And so we will, again, mostly ignore it in this course, but the realistic image synthesis course in the next semester deals almost entirely with this problem. So this secondary illumination, or sometimes called indirect illumination, or also global illumination, is really important, but is an advanced topic. Also, we are assuming that the space between surfaces is completely empty. And air is, for optical purposes, almost like empty. So we assume it's totally transparent, and so light that travels through space is not modified. Again, as I mentioned before, we will look at volume effects or participating media later in this course if we still find the time to do this. And finally, of course, we need a virtual description of a virtual camera. So that's the viewpoint, the position of the camera, the viewing direction, its field of view, the resolution of the film, the virtual film that records the light and things like that. Okay, so let's look, once we have such a scene description, how does ray tracing actually work? And the easiest way, we're in graphics here, is to actually show you an image to do that. So if we look at how light is being transported in a scene, right? So here we have our scene description. Here's our green surface, a box, a reddish kind box here. We have another surface here, which is reflective. We have a light source, and we have a camera. And just to be more specific, we're talking about an image plane. We often depict the image plane as being in front of the camera because it's more easily visible and you can explain it nicer. But in reality, this image plane, of course, is inside. If you really have a model of a real camera, then the image plane, of course, is inside, is on the back of the camera, right, behind the lens. But it's a one-to-one correspondence. We'll talk about this later. So you can think of the image plane really as the film that is inside a camera or on the back of the camera. And so all the light that enters through the lens is being projected onto this film. But again, it's easier to depict and sometimes also to think about the image plane of being in front of the camera. And so if you look at how light works in this world, then light sources emit photons. These photons, and we kind of have depicted here some rays, they travel along straight lines, at least in normal circumstances, right? Near a black hole, things are very different. But here, light travels in straight lines until it hits a surface, at which point it interacts with the surface. It can get absorbed, so it's turned into heat, and so it leaves our system. It's no longer an optical property, so it kind of vanishes. Or it's being scattered. And scattered could mean that, right, it's scattered into any other direction. And some of the light is probably scattered also towards the camera. And so it enters really through the lens and is projected onto the image. Oops, sorry. Come on. It goes through the lens and then hits the image plane. But again, we can visualize this as kind of going through a pixel on the image plane that is in front of the camera. And so this light then colors that specific pixel. But there, of course, there could be many paths that a photon takes before it hits the image plane. So for instance, light could hit this box here, then it's being scattered towards the mirror. And if it just arrives at the right spot and from the right direction on the mirror, it is then being reflected from the mirror towards the camera. Now, obviously, this you could do this, but this would be a very inefficient way of computing an image because, as you can imagine, most of the photons are either absorbed or they don't hit the camera, right? So you would do a lot of computation that would not contribute to the image. So that's not a very good. That's not a very good model. There's a question of whether we use the pinhole camera model. Yes, for most of the stuff we will use the pinhole camera model, but we'll talk about lenses and camera models later on, and we'll also talk at least about somewhat more elaborate models of cameras. So obviously, what we're interested in is this light distribution in a scene. And this is really a dynamic equilibrium, right? So at every point in time, we're pumping as many photons in the scene as are being absorbed, right? Because if that would not be the case, it would get brighter, right? There would be more and more photons, right? Or it would get darker if too many photons would be absorbed. So as you switch on the light, there's more and more photons pumped into the scene until the point where as many photons are being absorbed after so many bounces around in the scene that, right, you kind of end up with a dynamic equilibrium. And since light is so fast, this happens in an instant, at least on our time scale. Yes, so surfaces could also, there's a question on the chat whether a surface could also emit light source itself, emit radiation, like lava could be glowing. Yes, we absolutely do model that. Essentially, we would model the lava itself as a light source. And even though it is a light source, in general, you could also have reflection. So the lava could be illuminated. So it could glow itself, but it could also reflect light that maybe you shine a spotlight on the lava and that it gets even brighter. So in general, you have to take both into account, and we'll actually do this later on. So there's two ways of how we could simulate this light transport. The one is the physical thing that I just said, which we typically call forward light transport. So we shoot photons from the light sources into the scene. We scatter whenever they hit a surface. Whenever a photon hits the surface, we're scattering the photons, and then we wait until it eventually hits the camera or is being absorbed. Okay, and as I said, most of the photons that you would be simulating that way would not hit the camera and probably get absorbed. So that it can be very inefficient. So there are methods of how to make this more efficient. But generally, these methods are called particle and light tracing or forward light transport. A method that's typically more efficient is backward light transport, where essentially you do the thing in reverse. And you can easily see this as I go to the previous slide here. You could just turn these arrows around and you can say, well, let me start from the camera, trace rays or into the scene that kind of look for where photons would have to come from if they would illuminate this pixel, right? So essentially you trace a ray until, for instance, you hit this box here, right? And when you are at this point here, you can look up, is this point being illuminated? Would there be a path from the light source that illuminates this point? And if yes, how much light arrives here? And then you can take the scattering computation at this point and compute how much light would be reflected back towards the camera. And that method is ray tracing. So you start from the camera, you're tracing ray through every pixel on your image plane, and you look at least one ray per pixel, and you look at where would that light come from. And things will get a little bit more complicated, but that's the basic idea. It's this idea of backward light transport. And this is what ray tracing does. Forward light transport absolutely is possible. It is being used. And in particular, if you will come to the realistic image synthesis course next semester, we actually we'll also look at bidirectional methods that actually start from both sides. You start tracing rays from the light source and from the camera, and then you try to connect these partial rays to each other. And it turns out these types of methods are well, you have to be a little bit careful here, but they cover complex lighting situations in usually the best way. Again, we don't have time to go into details here. If you're interested, there is the course next semester. Okay, so ray tracing is a very fundamental rendering algorithm. It's automatic, so you can kind of see it's very, very simple, easy to understand, easy to implement. And the nice thing is it delivers correct images by default. While you have to invest a lot into making a rasterization algorithm do even simple things like shadows, they kind of are automatically included in ray tracing. It's very powerful and efficient as a method. It can easily deal with global effects like shadows and reflection and refraction, many other aspects. There are now efficient real-time implementation, both in software. This is what we've been working on for 20 years. But also now, since 2 years, in hardware. There's the hardware ray tracing extension that are already in current NVIDIA graphics cards, and they will be in all other GPUs starting maybe this year, latest early next year. There's a question, how do we know when to stop tracing a single ray if every surface would be reflective? Yes, you could set a hard limit and just say we do at most so many bounces. It actually turns out that you can do a stochastic method and terminate rays with a certain probability. It can, again, this goes into more advanced methods that we'll look into much more detail in the next semester. Sorry that I have to kind of refer you to for all the interesting stuff to next semester. It's actually called Russian roulette. It's a technique used in Monte Carlo simulation, and this is basically what we are doing for advanced rendering methods. Essentially, we're using Monte Carlo methods to solve the rendering equation, but we'll get there as we go along. So we have to cover a lot more ground until we get there. Okay, so we have real-time implementation in software and in hardware. It can be, you can kind of see that this is something that is often called an embarrassingly parallel methods, because you can essentially have a separate processor per ray that you're tracing. So it's extremely parallel. You can also distribute the computation easily across different hardware. It actually turns out, and we'll look into why that is, that that ray tracing scales logarithmically with the scene size, because we will build index structures to very efficiently find the triangles that may intersect with the ray. So while rasterization, at least in the naive method, is linear in the number of objects, so n here is the number of objects in the scene. Also, it is output sensitive and demand driven. So, right, if you are in a room with a closed door in a huge building, right, since we are tracing the rays from the camera, your rays will automatically terminate at the wall. And you will never even try to look what is behind the door. There could be gigabytes of data behind that. You would never look there, right? Look in quotes here. So that can be extremely efficient, which is really hard, which is kind of hard to do with rasterization. It's possible, but it's usually much less efficient. Also, the concept of light rays is not new. Actually, here in the top right, you see this image from Dürer from the 1525, from the Renaissance area. And you actually see him essentially doing ray tracing. So he has actually here on the right-hand side, he has a nail in the wall. He has an image plane, which is this frame here. And there is a vertical and movable vertical and horizontal bar. And what he does is, together with his helper here, he takes a small wire here and connects this nail here with a wire to a certain point in the scene, a point on this, what is it? It's a guitar here or something, Laute. And so then he adjusts the horizontal and vertical bars here to mark the point where that wire goes through the frame. Then he removes the wire, flips the paper back, and then he marks where that point on the object is being visualized or is being projected to on this paper. Right? So this is essentially tracing a ray from the position of the nail here through the image plane, through the image plane here into the scene to find out where things are being visualized, right? It's the same idea. And actually, even the Greeks with, for instance, Empedocles, even before Christ, have looked at this concept already. Also, ray tracing, ray casting is being used in lens design and in doing geometric objects, neutron transport, and many other applications. So it's nothing really new. So what are the fundamental steps in ray tracing? We kind of already went through them. First of all, we have to generate the primary ray. So at the camera, we have to generate a ray starting at the lens, going through the light, through the image plane into the scene. Or you can say, if your image plane is in the back, right, from every pixel on your film, on your image plane, from that point through the lens into the scene. So we have to compute this initial ray. And we typically do at least one ray per pixel. You can do more, and then you can kind of average, which kind of goes into Monte Carlo style integration methods, but we'll get there later. Then we are casting the ray. So this is, casting is to compute a single ray. And we will traverse a spatial index structure that we're building to, in order to quickly find the triangles that could be hit, or in general, we look at we mostly will look at triangles, but in general, to find the geometric primitives in the scene that the ray could intersect. And these spatial index structure help us to find these objects near the ray as quickly as possible. And because these are typically hierarchical data structures, this is where the logarithmic complexity comes from. So I have a description about this process in a second. So once we found a possible object that could be intersected with the ray, we compute that ray object intersection. And if there is an intersection, then we found a hit point. And what we're doing is we're trying to find the earliest intersection, right? We start from the camera and want to find the first object that the ray intersects with, because that's the only thing we are interested in, because we assume these surfaces are, something happens at that surface, right? Typically, these are opaque surfaces, so anything behind that surface doesn't matter anyway. If it's not an opaque surface, or if it's transparent, then light will be refracted, and we'll have to compute the rays that actually enter materials such as glass. And so we cannot use the original ray, but we will have to generate a recursive ray. So yeah, this ray casting now delivers us the first hit point, or the first point of intersection with any of the geometric primitives in the scene. And now we need to shade this point, which means we need to compute how much light is being reflected from this point in the scene towards the camera, right? Because that determines how to color our pixel. And so we're interested in the light power. Now, this is not a technical term. Really, we're interested in the term, the real term here is radiance, which is the quantity of light, and we'll talk about how we describe the amount of light, or this light quantity. So we're interested in the light power that is traveling along the ray. So how much light is reflected at this point, emitted or reflected, I should say, from that point towards the camera. And for being able to compute this, is we need to be able to do two things. The one is we need to compute how light is being reflected at this point. And we need to know how this point is being illuminated, right? Because, well, if it is a light source itself, then we can easily compute the light, which is kind of given by how we describe a light source. We can compute how much light is being emitted from a given point on the light source in a certain direction. This is part of the light source description. But most of the time, the object that's hit is not a light source. And then we want to know how much light reaches this point on the surface from any of the light sources in the scene. And the question is, how do we figure that out, right? So let's assume we only have one light source in the scene. We have to figure out how much light arrives at this point from the light source. And in order to do this, we're actually using ray casting again. We're tracing a ray from this hit point to the light source in order to find out if there's any other objects maybe in between, because then we have a shadow, right? So we trace a ray to find out if there is any object in between, in which case there is no illumination, at least if we assume that the surface is opaque. And otherwise, we know there is nothing in between the light source and that point, and then we can compute how much light is emitted from the light source towards the hit point that we're looking at. So we know how much light arrives at this point, and then we can compute, given the material properties, the scattering of light at this hit point, we can compute how much of that light is being reflected, how much of the light arriving from the light source is being reflected towards the camera. And we're essentially done in this case. Now, things can get a little bit more complicated, right? If you have a reflective surface, right, like a mirror, well, mirrors also reflect light from the light source directly, but most of the light actually comes from another direction. So, but again, we take care of this through ray tracing by tracing a ray in the reflection direction, right? If you have a mirror, you know, right, incoming direction equal outgoing direction. So then we essentially keep tracing a ray in the outgoing direction to essentially compute how much light arrives from that mirror direction. And the same we do for glass surfaces. We compute the refracted light direction, and we keep computing, recursively compute how much light comes from there. Okay, so here is the visualization of this process. So the first step was we generate a ray from the camera through every pixel in the image plane. Again, for visualization purposes, I've put the image plane in front of the camera. So here's one ray through one of the pixels. And so this is the ray tracing pipeline. Pipeline is not actually the correct name here because pipelines don't have loops here to go back, but let's keep this name here because it's being used in graphics a lot. So the first step is we generate a ray. So this is this step here. The next step is we're traversing that ray. So this is the ray casting process, or part of the ray casting process. So we're traversing this ray through the scene here, and you will understand in a little bit what's involved in this traversal process. And we do this until we find an object that could be intersected, like this green box here. And so here's this traversal process. So I mentioned that we'll actually be using an acceleration structure, as we often call it, or a spatial index structure. So here is, so this is a 2D example, of course. Here is one structure that is sometimes used. There's much more efficient methods, but here we're using a grid. So we're subdividing our scene into a grid. Now, typically this is a 3D grid. Here we're using this in 2D. And then for every grid cell, we are recording which object is actually contained in this cell, right? So in this cell here, we would record that this triangle is visible or is contained here in this cell. Of course, it's also contained in other cells. So a single triangle can, of course, be in multiple cells. And then there are cells where you could have multiple objects per cell, of course, right? That isn't really the case here. Well, maybe for this one, but it seems not. Probably could have an example where we have, I mean, but it's clear you can have multiple objects per cell. And so this traversal step actually now walks through the cells which are pierced by the ray, right? And so we only ever have to intersect the ray with objects that are contained in the cell that we're traversing as we as we're walking through the cells that are pierced by the ray. And it turns out you can do this traversal step, so finding out which of the cells you have to go through the grid. This is a process that can be extremely fast. It's just a few instructions, a few computations to find out what is the next cell. So you can do this very, very quickly. And then you only need to look, is there anything in the cell? No. Then you go to the next cell. Anything in there? No. Go to the next cell. So this can be extremely fast. And only if there is anything in this cell, then you actually say, okay, for every object that is in this cell, compute the intersection, right? Is there computing if there is an intersection of this ray with the object? Now here in this 2D example, right, we would do this computation, we would find out there is no intersection, okay? So the ray, even though there is an object in the cell, we're not hitting it. And so in this case, we simply, so we do this intersection computation now. If there's no intersection, we actually loop back and we continue traversing. Right? So we walk through all the others, everything's empty until we come to this last cell here, and now the object, the ray actually hits the object. So again, we do an intersection computation, and we have found an intersection now. And the intersection, we have to actually be careful because the entire object is in this cell. So there could be an intersection, but if it's not in the current cell, we actually have to continue traversing because there might be another object closer by, but that's a detail and we'll come back to this later. Okay, but here in this case, we have found an intersection. It actually is in the current cell. And so now we go to the next step, which is shading. Now shading is that process of computing how much light is being reflected towards the camera, as we just talked about. And so in order to do that, we first have to find out how much light actually arrives at this point, because in this case, it's not a light source, right? Otherwise, again, we could just compute how much light is being emitted towards the camera. This is not a light source, so we first have to figure out how much light arrives here. Now, in this example, we only have a single light source up here. And so how do we do that? We trace another ray, or we cast another ray in the direction of the light source. So this is the shading process, right? So now, and we generate a new ray here towards the light source, and we do the same steps, right? We generate the ray, we traverse the ray. If maybe we do the intersection computations. If there is no intersection, we continue traversing until we either reach the light source and there was no intersection in between, in which case we know there is no object that casts a shadow, or until we've hit an object which is not the light source, in which case we know light from the light source cannot reach the hit point that we're computing, so the point here on the green object. Let's assume there is no intersection, right? And so actually the light from the light source does reach this point. So we're back to this shading computation. So we can now compute how much light reaches this point here, and we can compute how much of that light makes it back towards the camera. Now, typically we only do one ray per pixel, but we'll talk about anti-aliasing and other techniques where you can have you actually trace multiple rays to essentially to do anti-aliasing and to get better quality. We'll get there, but a bit later in this course. So we now have computed how much light arrives at this point. We can compute with the material information of this object how much light is scattered back towards the camera. But there could be, right, if this is an object that is also reflective, right? So it's a green object, but let's say it's polished. So it also acts a little bit as a mirror. Now, in this case, we can deal with this by also tracing a ray in the reflection direction. So incoming direction equal outgoing direction, right? So the typical computation here of reflection direction. Now we're interested, so what is it visible in this mirror, right? So what light is arriving from this mirror direction? And now this query is exactly the same query that we did from the camera, right? So we wanted, as when we started with the original ray, right? We were asking how much light arrives at this pixel here along the ray. And this is exactly the same that we're doing here. So we generate this ray here, and we recursively query how much light arrives from this ray here. So we generate the ray, right? We traverse it as usual. We maybe do our intersection computations. We continue traversing until we found an intersection. And then we do the shading operation, right? So we're here at this point, and we do shading. We trace a shadow ray towards the light source, which again involves generating the ray, traversal, and intersection. Once we've done that, we're back here at the shading point. Now we know how much light arrives at that yellow point here. We can compute how much of that light is scattered back towards the green object. So this is this recursive computation. And then we know how much of that light is actually being scattered into the direction back to the camera. And let's say we're now done, and we now know the color of the original ray. Right? So we simply accumulate all the illumination along the rays that we've traced here. Is it guaranteed? The question is it guaranteed that the ray cast reaches the light source? No, it does not. If it does, well, I mean, actually, we're trying to reach the light source, right? At every hit point, we're tracing a ray towards the light source. So we're trying to connect to the light source, but it could be that all of the light sources are occluded, right? There's some object in between, in which case that object would be dark, okay? Would actually be black because it wouldn't receive any light. Now, typically we have some illumination via other surfaces, so the indirect illumination, not just directly from the light source. However, the naive ray tracing algorithm, as we're discussing it here, does not deal with this. So in this case, actually, we're only in ray tracing, the naive ray tracing, we're only considering the light that comes directly from the light source. And so if we cannot find a path towards the light source, there will be no light, and things will be black, right? Without light, there's nothing to show here. So obviously, right, if you have many reflective surfaces, you could go on forever, right? They could bounce around forever, the ray. So we either terminate after some maximum number of bounces, or I mentioned this Russian roulette technique, where we stochastically terminate the recursive computation after some number of recursion steps. Another question, what happens if we generate the ray directly towards the light source, even if the green surface was polished? Then you just hit the light source directly, and you could simply compute how much light is being reflected towards the surface itself. There is one step that makes things a little bit more complex. We'll talk about this later, but just to already mention it now, you must then not trace a light source, a ray towards the light source. right? Because otherwise you're counting that illumination twice. So you have to be a little bit careful here. But because we assume, I haven't really talked about this yet, but we assume, at least in the naive ray tracer, our light sources, we assume them to be point light sources. And since it's extremely hard, if not impossible, to hit a point with a ray, right? Because it's infinitely small. So there's zero probability of actually hitting that point. So that case doesn't really happen unless you are dealing with areas, light sources, which again, we will deal with in more details in the next semester. Okay, so if you visualize this a little bit more, right? So here we have our image plane, which now we've visualized behind the lens. So here is our lens schematically. We have a pixel on the image plane. So for every pixel, for each pixel, we're tracing a ray through the lens into the scene. And let's say we're hitting a glass object here, right? So we would generate a reflected ray because glass is reflective, as we all know. We would generate a reflective ray. Well, first of all, we would trace a shadow ray towards the light source and see, is there any light being reflected? And if it's not a perfect glass, there will be some light directly being reflected from the light source towards the camera. We will trace the reflected ray recursively, right? It will maybe hit some other surface, at which point we trace another. From this point, we trace a shadow ray towards the light source to see if any light directly arrives from the light source at this object, and then we can compute how much of that light is being reflected towards the first one, and we might recursively continue doing more and more, and we have to stop this at some point, right? Also, if this is a glass object, light might be refracted into the object, so we would continue also looking at how much light would arrive from that refracted direction, right? Because that also contributes towards the pixel. So we recursively also look for tracing rays here into the glass object until we hit the back of the glass object. There's another refraction happening. Maybe we hit some object here. We're also tracing shadow rays along the way, and we might recursively keep doing this. This is recursive ray tracing. This is the naive, basic algorithm of doing ray tracing. The difference between a shadow ray and a reflected ray is that a refracted or reflected ray, you're doing a full recursive computation, right? So you ask yourself how much light arrives along this ray, just as you ask with the initial ray here, right? From the pixel, you ask how much light arrives at my pixel along this ray. And this is the same thing here. At this point, you're asking how much light arrives from the refracted direction along this ray here, right? These are the full light. These rays do full light computations. The shadow rays are also rays, and but we are not interested in recursive computation. We are only interested, is there any object between this point here and the light source, right? And so we never start any recursive computation. So it's only, is there anything between myself, this hit point here, and the light source? And you can imagine, particularly if you have reflective and refractive objects, that you can build an entire ray tree, right? If you have many glass objects, the reflected light can again be reflected and reflected again. It could also be refracted, and I'll have an example in a bit. Okay, so this was more the top level description of that. We can also kind of semi-formalize this. So tracing a ray, right, that algorithm consists of searching for the next intersection along the ray. That would return the hit point as well as the material. So we need the material at that point because we need to compute how much light is being reflected and what color is that material. And then when we found that hit point, we return how much light is reflected. And in order to do that, we compute the shading. Given this ray, the ray that hit this hit point, the hit point, and the material. Now this is another function here. So this function gets the ray, the hit point, and the material. And it iterates over all light sources. It tests, so it traces that shadow ray, the ray towards the light source, and it needs to know how far away the light source is, because you only want to check along the ray until you arrive at the light source. You're not interested in any objects behind this, right? So the distance to the light source is important here as well. And if there's no hit point here, there's nothing in between, then we calculate, right, how much radiance arrives from the light source and how much of that is actually being reflected towards the original ray that generated the hit point at which we're doing the shading computation. And we do this for every light source, right? For every light source, there could be some light that arrives at that point, and then we can compute how much of that is reflected. Then if the material is a mirror, has a mirror component, so it's polished and it does reflect light like a mirror, then we can also trace a recursive ray, right? So we call this trace procedure, that was the very one here at the top, with the reflected ray. So here we're computing, right? This trace function gets a ray, and here we compute the reflected ray. That given the original ray, right, and the hit point, we compute what the reflection looks like, the reflective ray looks like, and then we're tracing this reflected ray. And again, then from that trace function, we get back how much light arrives from that reflection direction, and we add this mirror component, this radiance we're getting from there. We look how much of that light is being scattered to the original ray, and so on. And we can do the same for any transmission or refraction, and so on. And we had this example in this question with the lava. So if the object that we hit also is a light source, right, then we also add the illumination from the light source, right, through the emission from the object itself. And then we add up the components that arrives from each light source, plus the mirror component, plus maybe the transmission component, plus maybe the emission component. And that is the amount of light that is finally being returned to whoever asks for how much light arrives from this given ray. And then this shadow trace operation, right, is right, this was the function that we kind of called here, right? We return false if there is an intersection at a distance closer to the distance of the light source. I guess there is actually an error here. No, it's correct. So we return false if there is an intersection that's smaller than the light source, because then there is no illumination, so this if statement here wouldn't do anything. Otherwise, it returns true, and we return, and then we're computing how much light from the light source actually is being scattered. So in general, right, we're assuming if we hit an object, it's on an opaque object, and so we stop, right? We assume it will not let any light through it. Now this can be handled with if there is a transparent object. However, not if the transparent object actually changes the direction of the ray. Can anyone guess why that doesn't work? If the object actually refracts the ray and so changes the direction. The medium is changed, that's correct. But that's not, I mean, if the other medium has the same index of refraction, then the direction would actually be the same and it would still work. Feel free to also use the audio channel to answer. Anyone has an idea why that would work? Well, remember, maybe we would never stop then. No, that's not the right answer. No, the problem is, right, if at the object that you hit before you hit the light source, because refraction of the light source will illuminate that surface. Yes, yeah, no, but the real reason is if the direction changes at the object that is between the hit point and the light source, you don't know where you have to shoot the ray to, in which direction you have to shoot the ray, such that after it's being refracted and after it has changed the direction, it will arrive at the light source, right? Because if you shoot towards the light source and the direction changes, it will not actually get to the light source. So it will not answer the question, is there an object between you and the light source, because you actually don't do the right computation, right? So, right, this ray to this light source, that doesn't work in this case because you don't know which is the ray to the light source, okay? Okay, so the shading computation now, yeah, I mean, we kind of went through this. I just want to go into a little bit more detail here. So we have different, we kind of discussed this. We have different materials. So we have diffuse objects. So these are objects that scatter light, any incoming light is scattered in all directions the same. And so if you look at a white wall, right, its brightness doesn't change if you look at the same spot from different direction, right? So white walls are good examples of mostly diffuse. They're mostly diffuse. So a good example for diffuse surfaces or diffuse reflection. So, but again, there are other surfaces like a mirror surface, right? Because depending on, if you look at the same point on the mirror from different direction, you actually have very different illumination because you see whatever is being reflected now at this point, and that obviously depends on from which direction you're looking at this point. And the same is true for glass because right, the direction changes and you will always see something else depending on, so the illumination will change depending on which direction you're looking at, even if it's the same point on the glass surface. There's also more complex surfaces, and we'll talk about this in much more details, where you can physically measure and describe how light is being reflected on the surface. So there's what is called a bidirectional reflectance distribution function, a BRDF, and we'll go into more details a little bit later, that describes for how much, at a given point, how much light of a certain that arrives from a certain direction, how much of that light is being reflected in a certain other outgoing direction, okay? And this distribution or this scattering function, if you want, that describes the optical properties of our surface. Again, we'll go into this in much more detail a little bit later. Right, and in terms of material illumination, we already mentioned, right, there's point light sources, so light that is emitted from a single point. We also have this concept of a directional light source. It's also light from a single direction, but it's called directional light source because they're only defined by direction. So it's kind of parallel light that arrives. In first approximation, the light from the sun is the directional light source because it only comes from essentially one direction. At every point, it is illuminated from the same direction, right? Because of essentially the sun is so far away. We can also have area light sources. Now, how do we deal with them? Again, we will mostly ignore it in this semester, but just as a outlook of how you can do it, you can essentially approximate an area light source with many point light sources, right? And you can actually do this stochastically by choosing a random point on the area light source each time. And if you do this over not just a single point, but average over many points, you get the correct results. We'll have an example on this in some of the later lectures. And then there's also the indirect illumination. Remember that at each hit point, we only computed the light that comes directly from the light sources, or the light that comes from the reflective direction if it's a mirror, in the refractive direction if it's a glass surface. These are only two, right, individual directions. Of course, light could arrive from any other directions on the hemisphere above that point, right? And it typically does because, right, in every room, light scatters from all the other surfaces as well. So that, again, this is the indirect illumination or the global illumination. Again, we will ignore it in this semester here, but if you really want to compute it, this is quite expensive, or can become quite expensive. But there are ways to deal with this. Okay, there's a couple of other approximations that we're typically do in rendering. So typically light, and we'll talk more about this later, we have a full spectrum, right, with the full rainbow colors from ultraviolet, bluish kind of colors through the yellow and greens towards red and the infrared spectrum. We would have to do the computations for each point in the spectrum. We typically don't do this, but we take three samples, a red sample, a green, and a blue sample. So one at the red end of the spectrum, one at the blue end of the spectrum, one in the middle, which is typically where green is. And so we essentially only approximate the spectrum with three colors. When we talk about color later in the semester, you will see that this actually corresponds, you can rationalize why this actually works, because also our human visual system actually works in a three-dimensional color space, which is not exactly RGB, but you can argue that we only have 3 degrees of freedom for color. However, this approximation actually is not exact, and so it's an approximation. And we'll talk about why this can fail. Also, right, as I already said, light doesn't only come from a finite number of point light sources, right? You could have the full indirect light, so it's coming from all possible directions, and there's infinitely many. So the question is, how do we deal with that? We don't just have diffuse, specular, and mirror and refractive materials. We also have something like an ambient, which is approximation. We'll come to these class of materials a little bit later. And then also how light is being reflected, right? This can be extremely complex, and it can depend a lot on the optical properties of the material. In graphics, we often use approximations there, empirical models like the Phong or the Blin-Phong shading models, and we'll talk about how they work. But there are also physically accurate reflection models, or material models are available. But we will not go into too much details there because it's often not needed. So if we now look at ray tracing incorporates a number of features into a single framework, right? Remember, there's some questions that I overlooked. Oh no, this was the answers to the previous question. Okay, I went through them. So remember that when you had vector displays, you had to actually actively compute what surfaces were hidden, or what lines that you were drawing were hidden behind other surfaces, right? We don't have to do this with ray tracing because the ray always because of how we query for the hit point, we will find the first hit point, and we'll go through this in more detail in a second. And we do that computation front to back. So we'll find the first intersection, and we will ignore anything behind it. So by definition, everything that is hidden or is obscured by some other objects will never show up in your image. Also shadow computation, right? With the shadow ray that we're tracing or casting, we implicitly include shadow computation, right? It's just another ray that we're tracing. And we will have exact simulation, at least of some light path, right? So again, global illumination is not included, but the direct illumination from light sources is included, and it's kind of excluded accurately. However, there's some limitations, right? We could have many reflections and refractions, and we actually could get an exponential increase. So if every surface has a shadow, has a reflection ray and a refraction ray, so if every object is glass, let's say, right, you have an exponential increase in number of rays as you recursively trace these rays, which can be extremely costly. And so and we'll find out later that there are methods like path tracing that can deal with this. And again, we'll go into this in more detail in the next semester. Also, like with the naive ray tracing or the simple ray tracing that we're discussing here, we're only tracing rays directly towards the light source. We ignore indirect illumination because that would be way more difficult. And again, path tracing is a method to do this, and we'll look at that later. Okay, but even though there are many limitations and some of the things that are approximations, we can generate extremely realistic looking images. And here's actually some of the images from earlier rendering competitions. So you, in your exercises in the rendering competition this semester, you will be able to do images like that with the ray tracer you're building in the next couple of weeks. So you will be building this as part of the exercises. What is possible? So here's actually one of our first images when we started to have real-time ray tracing. And we talked to some, at the time, this was 2001, we talked to some people in the car industry because they had problems visualizing cars. I mean, visualizing the body of a car. Yes, you have a lot of reflections on the car surface, so exact reflections that ray tracing can do would be nice. Also, right here, you see the reflection in a curved surface of the back of the mirror here. But most importantly, at the time, they wondered how to actually accurately render the headlights of a car, right? Why? Because the headlights of a car are kind of the eyes of the design of a car, the eyes of a car. And so you have to design them, and they have to look right if you want to sell your car, if it should look good. And with rasterization, you can't actually do this in any meaningful way. Why not? Well, if you look at the headlight, so this is the left image here. If, for instance, let's take a pixel down here, right? If this pixel on the image here, if you want to know what color does that pixel have, right? So if you trace your ray from the camera into this scene here, you're hitting the outside of the front glass of the headlight, right? There's some reflection of light from the environment, but most of the light, because it's glass, it's transparent. So you have to compute the refraction direction, right? So the glass is being refracted into the glass of the front glass here. So you do that, and then you hit the back of the front glass. And again, there's a refraction. Now you're inside of the headlight. Now you keep tracing this ray, and it will hit the reflector, right? And the reflector is almost 100% reflective. So you compute the reflected ray, and that ray will actually maybe hit the the lamp here. Now the lamp is included into yet another layer of glass. So hit the outside of the glass. This is almost 100% transparent. So you do a refraction. You're now inside the glass, the glass that is around the filament that's actually generating the light. Then you trace that ray. You're at the back side of this glass. Now you're inside of the lamp, right? Let's say you're not hitting the filament, so you're hitting now the inside of the other side of the lamp. You do a refraction, then you're at the outside of the glass, again, 100% transparent, almost. You keep tracing, now you're inside the lamp. You're then hitting the reflector on the other side, 100% reflective. Then you reflect towards the top, let's say here. You hit the inside of the front glass, you refract, you hit the outside of the front glass, and now your ray actually goes into the environment, and it may be hitting whatever object is around the car, right? Maybe a tree or a person, or in this case, some other geometry. So in order to just visualize a single ray, you have to trace dozens, if not many more rays, before you even figure out how much light makes it towards the camera. And this is extremely costly. And at the time, we actually had 4 fast processors. This was in 2001, so you couldn't even do it on a single machine. And we were able to render these light sources, the headlights of a car, at about 2 frames per second at video resolution, which is 640 by 480 at the time. And there was simply no other method that could visualize headlights. And at that time, when we showed this at a conference, so we were invited, we showed this at a conference. And in the next 4 weeks, we had the entire car industry visiting us here in Saarbrücken, because they all wanted to see how we can do it, and wanted to actually use this technology. We eventually worked with Volkswagen. This is actually in the Volkswagen Visualization Center. I think I have another image of that. So we actually founded a company that installed this technology at the Volkswagen Corporate Visualization Center in Wolfsburg. But we also worked with Audi and many other companies, car companies. We actually showed the technology to Airbus. It was distributed, it was shown across 4 different locations in the US. So this was an amazing time back then. As I said, nowadays, this is becoming kind of commonplace. We worked on the realistic visualization of cars. Of course, these are spline surfaces here. So we worked on how to render not just with triangles, but actually with NURBS surfaces. We looked at AR, VR. So this is, some people who have been in Saarbrücken already might recognize, this is kind of the foyer of the lecture hall building. We put a fisheye camera here in the middle, which recorded in video, recorded what's happening around this spot. And then we virtually put, so we took the background image and we put a virtual car here. And now we could compute what would be at least approximately visible, what would reflect off of the car, because we recorded what's around. What's around here, and we can actually, you would actually see that person walking by. I don't have the video here; it's just a still image. Also, lighting simulation, right? So indirect illumination. You see here the smooth shadows, and also the corners are getting dark if you do accurate visualization. Or here, something that's called caustics. If you next time you're at the dinner table and you're enjoying a glass of wine, or tea actually works equally well, you might see these, that the rounded surfaces essentially act like a lens, and they focus the light from the light source onto onto other surfaces, and they can be very intense, these things. And we showed how to do that. We also, I mentioned that the ray tracing is logarithmic in the complexity of the scene. So we also looked at huge models. Here's a scene with 1 billion triangles. Or here, this power plant was the first one, 30 million triangles. It was huge at the time. We also looked at very, very large outdoor models. So this is 80 by 80 square kilometers. Actually, if you compute it, about 90 times 10 to the 12, 90 trillion triangles. And so the green here on the back, I mentioned this last week, the green here on this hill is not just a green texture, but actually all trees that were computing. And this was at the time running also at 2 seconds per frame in this case. This runs much more efficiently now. This was 2003 or so. We also worked with Boeing. I just mentioned that. So we had this Boeing model with 350 million triangles, individual polygons, a huge data set, and this made it possible to actually talk with Boeing. We did volume visualization, and there was an entire new research field that kind of started to establish itself called real-time ray tracing. And we also started to look in how could you use ray tracing in games. So some of our students actually implemented a gaming environment. At the time, you can see here, this was actually demonstrated in GameStar, which is a gaming journal. And you could do fun stuff like this portal here, which would transform a gamer to a different location. You could essentially look through that portal, because whenever our ray hit the portal surface, right, we essentially transformed the rays to that target location and continue tracing the ray there, which is a fun effect. And now that was 2006. We published that. But now you can actually run commercial games on the current NVIDIA graphics cards, and some of the games actually have ray tracing effects today. They run in more or less real time. Still somewhat expensive for some of the games, but you can actually have this functionality available in games. And there is a clear statement from NVIDIA that they are working towards fully ray-traced games going forward. Now, today's games are still using rasterization for most of the rendering, and then they ray trace some of the additional advanced effects using ray tracing. But the goal definitely is to do more than that. How much of that rendering is through ray tracing? That depends very much on the game. Sometimes it's only the reflection effects or some special shadows. Sometimes they mix some tricks in rasterization with a little bit of ray tracing. So there's all sorts of ways of how this can be included. So there's no simple answer for that. So in the past, until the end of the 90s, ray tracing was a purely offline technique because it's just way too expensive. And so it was used in the film industry, and even in a single image there would use hours. And so it wasn't actually used much in the film industry. Most of the rendering in the film industry was still using rasterization. There was only some specialized effects that were done with ray tracing. And that was until the 2012 or so, when suddenly, within a single year, the entire film industry switched over to using ray tracing. There is usually the initial pass in rasterization, and the light is sampled with a couple of rays and then denoised. Yes, that's one way of doing things. There's other ways. Denoising is an important part. We'll talk about this later. Oops, sorry. Yes, also it was believed that you couldn't actually build hardware for ray tracing because people had tried the 10, 20 years before that and it didn't work. And then more recently, actually the very first paper on real-time ray tracing was by Stephen Parker from the University of Utah in 98, but it was published not in a graphics journal, but at Supercomputing. And so it wasn't widely recognized. And then in 2001, we published the first interactive ray tracing papers here. Ingo Wald, which was a PhD student of mine, also distributed real-time ray tracing, so some of the lighting simulation on clusters. We actually did the very first hardware implementation, which we published in 2005. And then and talked about this last week, there's now a commercial implementation like Embry and Optics. Embry from Intel are only running on CPUs, and Optics running only on NVIDIA GPUs. Right, and as I mentioned, the complete film industry has now switched over to using ray tracing-based methods, in particular Monte Carlo path tracing or advanced path tracing method. We have our own conferences, which started off as a symposium of interactive ray tracing, which later merged with another conference into high performance graphics, which actually next year will take place in Saarbrücken. We're preparing this right now. There is a research ray tracing system, so there's PBRT. I mentioned the book already, physically based rendering. So that's what PBRT stands for. Physically based ray tracing, actually. There's Mitsuba 2, which is a renderer out of EPFL. And we have our own NEDSL-based ray tracer, which we published last year. Which is very fast because it can run on the GPU and the CPU and can actually be used both at the same time. And it actually, on each of those, on the CPU and the GPU, it is faster than both Optics and Embry on the respective hardware. There's also kind of products. There's, of course, Blender, which is an open source tool. So it's an open source product if you want. It also has an advanced ray tracing based system. As well as Eevee, which is a rasterization-based renderer. There's V-Ray from Chaos Group, who collaborated with us. There's Arnold and Brett from Autodesk. The Corona renderer, which I mentioned last time, the unfortunate choice of name, at least in today's environment. And Mental Ray, and many, many others that I don't list all here. So Kartik is asking, does ray tracing take the pixel-to-pixel approach as opposed to object-to-object approach in rasterization? Absolutely, yes. And we'll talk about this a little bit later. Yes, in ray tracing, you iterate over the pixels, and then you want to find out which object is visible for that pixel. Where in rasterization-based approaches, you render each object separately, so each triangle. And then for each triangle, you want to figure out which of the pixels are being covered by that triangle. And we'll discuss in more details why this is more difficult in rasterization. Rasterization is more amenable to hardware, but for advanced effects, it's much more difficult to do those in rasterization. By the way, ray tracing is not only used in graphics, but also outside of casting. So it's essentially, if you think about ray casting as a query, so is there anything along this ray, right? Or how far is it to the next object along the ray? And that can be used for visibility computations, which are sometimes important. Radar, you can do radar and sound wave simulations with this approach. If you add some wave effects to it, you can compute the volumes. If you have a very complex geometric shape, geometric object, and you want to know what is the volume of this object, right? Can actually be quite complex to do this. The most simple thing you can do is actually tracing a set of parallel rays, each representing some fixed amount of area through that object, and you simply add up numerically. Essentially, you're numerically integrating the volume of the object. And if you can do ray tracing really fast, then this is a very, very simple way, for instance, to compute the volume of an object, which otherwise could be quite elaborate to deal with. You can also do collision detection and many other things with ray tracing, but we're essentially using it here in this course. We're only using it for rendering. On the research side, we're investing right now a lot into radar simulation as well and advanced lighting simulation. So I was a little bit slow today, and so we only have a couple of minutes left now. By the way, is there? I did it without a break today. So if you would prefer to have a break after 45 minutes before we continue, let me know, and then we can change this. On my side, I like it more to kind of do the hour and a half in one piece, but let me know if you disagree. Use the email list, or you can also send comments here. So since we don't have much time, we will have to follow up on the ray primitive intersection computations in the next lecture. So I have to hurry up a little bit, I guess. Are there any questions remaining at this point in time? We have a couple of minutes left to discuss them. Feel free to use the audio channel as well. Important message to all students tutoring. Okay. Some of you have not filled in the form for picking time slots for tutoring. Please do so now after the course. The form is available on Teams. There is a post called Exercise Groups and Tutorial Slots in big red font. Click on See More to get the link. Thank you. This is from Hugo. So please look at that, and hopefully this was, you should have received an email. How do you make sure if I submitted the form? Well, if you haven't submitted it, just submit it. Again, we will sort this out. If you're not sure, well, you should know whether you submitted or not. If in doubt, submit it another time, and we'll take care of that. Any other questions? Okay. Team is actually clever. So if you tried, we'll tell you you already did. So hopefully that information is fine. Only one form per team. Hugo will be able to answer that. I don't know. One per person. So that might explain why maybe some people have not submitted in. Which follow-up book should we read for this part? There is the Introduction to Ray Tracing by Steve, not Steve Parker. Missing the name right now. Look it up. I showed the. I am bad at names. I'm blanking on the names. Introduction to Ray Tracing. Peter something. No, Andrew Glussner. Oh, sorry. Yeah, there's also the book by Andrew Glussner, but that's an advanced book. Yeah, the work by Peter Shirley. Thank you very much. I have a bad memory for names. I know exactly the face in front of me, but anyway, yeah, Pete Shirley. Any other questions? So in summary, in ray tracing, we're generating a ray, and we are following its path until it reaches the light source. And if not, it either but in addition, we might also follow the reflected and refracted light rays. We might generate additional rays that we are following. This is where you can get this exponential increase, right? If at every surface you're actually tracing more than one ray. Can we contact you about research and working in this field or in your research group? Absolutely. I mentioned this last week. If you're interested in HEVI jobs or a bachelor or master thesis, or if you're that advanced, also maybe looking for a PhD position, let me know. We're always interested in good people. So yeah, contact me and I will usually forward this to the different groups. So we're working on AI, on graphics, of course, as well as in high-performance computing. But specifically, since this is a graphics course, I guess most of you will probably be interested in graphics. But we offer topics in all of those areas. So I will forward that to my team leaders usually, and because they know in more detail what we can offer. Okay. Any last question? Otherwise, we'll just close this down. Thank you very much for attending. And I don't see another question. Thank you very much. And we'll see you on Thursday then. Bye-bye.